Working with large formulas is all about staying organized. And one of the largest formulas you might ever have to work with is the correlation coefficient, which is featured here. Consider the original data in scenario 2A. What is the coefficient of correlation and the coefficient of determination for the linear relationship between the number of clients and the actual number of courtesy van transports? Okay, well, wait a minute. Stop. The correlation coefficient. It's a single score for the strength of a linear relationship between two sets of data. Oh, right. And in the scenario before, we were looking at two sets of data. They were concerning the number of clients on a contract and the number of transports. And I have the scratch work from the earlier scenario. That was the data right there, right? Total clients was X, total transports was Y, and then there was all of this workings here because we were finding the linear regression equation. Now it is time to follow up with a score of the strength of the linear relationship between those two particular issues being discussed earlier. Oh, right, and actually what we need to do, if you have the note frame, is already printed here. The correlation coefficient, also known as rho or R. Oh, all we have to do is fill out that big long formula right there. Okay, big formulas are all about just staying organized. This is the correlation coefficient. Remember, coefficient is just another word for number, and when we are done filling out this formula, that's what we will have. We'll have a single number. Oh, what we need to do is find all of these pieces. And actually, we have most all of these pieces from scenario 2A. Remember how I saved the scratch work from scenario 2A? Because, for instance, in scenario 2A, we learned that in the data, there were 7 different contracts. That was these rows right here. Oh, right, n equals 7. From last time we worked on this, we learned that the sum of X, the total number of clients across those 7 contracts, was 7,400, or 74,438. From last time, this is stuff we figured out already. The sum of Y, the total number of van transports, that was 7,560. Now see, this is work, X and Y, that we already did last time when we were finding the regression equation. Although, you might be thinking, no, wait a minute. I remember last time we did have to fill in some formulas, not as big as that one that we just looked at on this sheet. We did have to fill in some formulas, but I don't remember finding a sum of X or a sum of Y. I don't remember from the last scenario where that fit in. Oh, yes, but you know, remember we found X bar and Y bar, the average X and the average Y. This was in the last scenario. In finding the average X and the average Y, we had to first find the sum of X and the sum of Y, and that is what is, notice, useful here. Because all we're trying to do is just find the puzzle pieces. That, for instance, is N. There's the sum of X again. There's the sum of Y. We have that from last time. Now, also from last time, might as well save ourselves some work. We calculated the sum of X times Y, meaning multiply each number of clients by the number of van transports they requested and then add everything up. We got a rather large number, 122,198,041. That's work we did last time, and notice that that would be helpful this time because that's right here. And what else did we do that could save us some work? Oh, last time we did have to find the sum, sigma, of X squared, meaning square all the different numbers of clients and then add them up. And that added up last time to a really big number, 1,194,000,000, then 980, then 641. And sure enough, we do need that down here. See it right here? We're going to need that for the formula. Okay, now that is all summary statistics. That's what the little puzzle pieces are called, summary statistics, that we already had on hand because of the work we did in scenario 2A. To complete the correlation coefficient, the big formula we're looking at now, we need one other additional puzzle piece. Notice that we never found last time the sum of y squared, and we need it this time. That's why there's some scratch work here. The total number of transports required annually by each one of those contracts. I am just copying the data that we were supplied originally, 292, for those 7 contracts. 203. Okay, this is all data that we were originally supplied. What we need to do ultimately to finish out the formula is, well, similar to work we were doing in scenario 2A. Take each one of these numbers here and square them. See how over here it says y squared? This was y. Oh, all right, when you do that, you get some very, very large numbers. Now, let's see if I can do this neatly, because it is quite a bit of arithmetic if you do it manually. I'm going to draw myself some lines. Here we go. Let's see, 1042. If you square it, I get 1085764 on my calculator. Okay, a million some odd. 2,560, if you square it, 6553600. 149, if you square it, 22,201. 186, if you square it, 34596. 192, if you square it, 85264. 1,128 squared, 1272384 over a million, and then 2,203 squared, 4825. Oops, that's a 5. 4853. 209, 209. Now, why did I do that? Because I want to add up these numbers, basically. Add them all up. I added them all up. I got 13,907,018. Why did I do that? I'm still trying to find what was asked for above, and that is right there. The correlation coefficient, that's the one last piece that I need. Oh, all right, now, we have all the pieces that we need, although we haven't actually answered any of the questions that were asked. Right, because first it asked for the coefficient of correlation, or the correlation coefficient, and then it asked for the coefficient of determination. Hang on to that thought. First, we're just working on the correlation coefficient, which is this particular formula here. When we put those numbers in place in that formula and do those calculations, we will get back a single number that is between 1 and -1. Because I said, you might want to note, correlation coefficient, score of the strength of a linear relationship. If the one number that you finally get is close to 1, positive, powerful positive correlation. Oh yeah, these two things seem to move together. And then if, wait a minute, the number comes out to be pretty close to -1, powerful negative correlation. Oh yeah, these two things seem to consistently move in opposite directions. Now, what is it in this case with the clients and the number of van transports? Well, let's fill in the formula. Let's fill in the formula. Okay. First, just the numerator. I'm working on piecing together the numerator. N is 7. 7 times, okay, this is the sum of x times y. Remember that that was the 122198041. Remember, it's all about staying organized. Minus the sum of x times the sum of y. The sum of x was 74438 times the sum of y was 7560. Okay, remember order of operations. Do that multiplication, do this multiplication, subtract this out of this, except, wait a minute, that's just the numerator. That's just the numerator. Now let's piece together the denominator. Okay, first, right in here, n is 7. 7 times what? 7 times, this is the sum of x squared. Now that we had found last time, it was a very large number, 119498061, right? Just goes right there. Minus the sum of x squared. You go, wait a minute, what's the difference between these two? Okay, this is where you square each of the x's and you add them up. This is, notice where the parentheses, where you add up the x's and then you square the result. You add up the x's, that's the 74438, then you square that. That's what's going on inside these parentheses. And then wait a minute, when you have that result in there, you multiply times 7. Remember, big formulas, just stay organized. And multiply that by, basically, the same thing in y, so to speak. 7 is the n. 7 times, now wait a minute, in the brackets, grab the sum of y squared. That's what we just worked pretty hard to find manually. 13907,081 minus the sum of y squared. The sum of y was the 7560. Square that before you subtract it out of this, then multiply it times 7. And then wait a minute, it's this overall multiplied times that. And before you say, yay, I have the denominator, remember, all of this goes under a big square root. So remember to take the square root before you then divide that into the numerator. When you have done that, you will have a single number. And I did that. Oh, and if you want to check me on this, I get that the numerator, right, piece that together, is 2,092,635,007. Okay, that's just the result of the top. Divided by, once you take the big square root of all that's going on in there, I get 336,906,625. Say, oh, great. Yeah, but divide that into that, and sure enough, it is a number between 1 and -1. Basically 0.869. There is our first answer right here. That is the, let me label it, correlation coefficient. And what's that supposed to mean now that we have it? Well, 0.86, that's pretty close to 1, implying that there is, in that original data with the 7 contracts, there does seem to be a fairly powerful positive correlation. That sort of makes sense. The more clients are served by a contract, the more van transports they request under that contract. Okay, we've confirmed that mathematically. Oh, but we haven't finished with this scenario because it also asks for the, let's review, coefficient of determination. You go, oh no, we need like a whole nother formula? No, not really. The coefficient of correlation, that's what we just worked on. Traditional symbol is R, or rho, basically. The coefficient of determination is nothing more than that number squared. Oh, the coefficient of determination is often referred to just verbally as the R squared. It is another score of the quality of the linear relationship between the x and the y that you're working with, but it is the result that we just got squared or multiplied by itself. So, see, this won't take that long. We can answer the second half of this. This is the correlation coefficient. I just take that number and I square it. I get 0.755. That's the coefficient of determination. The so-called R squared. Determination. The other half of what was asked. Right there. So, the R squared, the coefficient of determination, was 0.755. You say, okay, well, I get what the correlation coefficient is all about, but what is this R squared about? Okay, the correlation coefficient is the strength of the linear relationship. The coefficient of determination, you might want to note this, has an additional value, interpretation, if you will. The coefficient of determination, the R squared, you can interpret as a percentage. The 0.755, basically about 75%. You say, okay, 75% of what? Okay, here it is. We have just found out from the R squared that about 75% of the variation in those 7 contracts we were looking at is explained by the original linear regression. About 75% of the variation in van transports appears to be explained by the number of clients. That was the X. You say, well, what about the other 25%? The other 25%, we don't know. We haven't found an explanation yet, okay? But about 75% of the variation we are looking at does appear to be explained by the number of clients. So the R squared will be between 0 and 1. The correlation coefficient between -1 and 1, and the coefficient of determination between 0 and 1.